The world's coastal cities are sinking, and traditional seawalls are no longer enough to stop the rising tides. But what if we stopped fighting the water and started living on it? By utilizing advanced modular honeycomb pontoons and dynamic mooring systems, we are finally engineering a way to build permanent, stable civilizations directly on the open ocean. Welcome back to Civil Engineering Edge, where we explore the future of infrastructure, structural resilience, and next-generation construction technologies. Today's topic is not science fiction. It is not architectural fantasy. It is one of the most urgent engineering challenges of our time: how to build cities that float. Across the globe, coastal megacities are facing irreversible threats from rising sea levels, land subsidence, and intensifying storm surges. Traditional civil engineering solutions like seawalls, embankments, and land reclamation are proving to be temporary defenses against a permanent problem. As professional civil engineers, researchers, and students, we must ask ourselves a bold question. If water is inevitable, why not design for it? In this episode, we will explore the engineering principles behind floating cities, focusing on hydrostatic equilibrium, buoyancy stability balance, modular honeycomb pontoons, and dynamic mooring systems. We will bridge theory with structural feasibility and examine how floating infrastructure may become the most resilient foundation for future civilizations. Let's begin. The reality of rising tides. Global sea levels are no longer a distant environmental prediction. They are a measurable engineering reality. According to long-term climate observations and oceanographic data, global mean sea levels have been rising at an accelerating rate over the last 3 decades. The implications for civil infrastructure are profound. Coastal regions are economic powerhouses. Over 40% of the global population lives within 100 kilometers of a coastline. These regions host ports, industrial corridors, airports, highways, power plants, and dense urban settlements. Yet, they are simultaneously the most vulnerable to storm surges, tidal amplification, and saline intrusion. Cities like Jakarta are sinking due to groundwater extraction and soft soil consolidation, compounding sea level rise effects. Miami experiences recurrent tidal flooding even without storms. Shanghai faces storm surge risks in one of the most densely populated deltas on Earth. From a structural perspective, the challenge is not just rising water levels, but dynamic loading from waves, tides, and extreme cyclonic events. Conventional foundation systems, isolated footings, raft foundations, and deep piles depend on stable soil strata. But what happens when the soil itself becomes unstable due to erosion, liquefaction, or prolonged inundation? This is where traditional land-based engineering reaches its limitation. We are trying to anchor permanence in an increasingly fluid environment. Floating cities shift the design paradigm entirely. Instead of resisting hydrostatic forces, we embrace them. Instead of rigidly fixing structures to soil, we allow controlled movement through buoyancy-balanced platforms. By analyzing Archimedes' principle, center of buoyancy, metacentric height, and dynamic stability under wave excitation, engineers can design habitable structures that adapt rather than resist. The rising tide is not just an environmental crisis, it is a design challenge demanding innovation. Reviewing current 2026 satellite data on coastal erosion and displacement risks. By 2026, satellite-based Earth observation systems provide unprecedented clarity on coastal transformation. Data from missions such as NASA and European Space Agency reveal accelerating shoreline retreat across multiple continents. Satellite altimetry measurements indicate consistent global sea level rise trends, while synthetic aperture radar SAR imagery highlights coastal subsidence in delta regions. Thermal imaging and ocean salinity mapping show expanding saltwater intrusion into freshwater aquifers directly threatening municipal water supplies. Major urban hubs face immediate displacement risks. Low-lying island nations in the Pacific show measurable land loss. Delta cities experience both vertical land subsidence and horizontal shoreline erosion. Industrial port zones face repeated flood damage, disrupting global supply chains. By integrating satellite-derived digital elevation models, DEMIS, with predictive hydrodynamic simulations, engineers can now model 50-year and 100-year flood scenarios with improved precision. The alarming conclusion: many coastal infrastructures were never designed for the magnitude and frequency of flooding now being recorded. From a civil engineering standpoint, these data sets are not merely environmental indicators, they are design inputs future infrastructure must account for. Higher baseline sea levels, increased storm surge heights, stronger cyclic wave loading, extended flood durations. Satellite data confirms a critical insight. Retrofitting existing coastal defenses may not be sufficient in highly vulnerable zones. In several metropolitan regions, managed retreat or adaptive infrastructure may become more economical than continuous repair and reinforcement. Floating infrastructure emerges as a strategic alternative. Instead of constantly elevating land-based structures, floating systems automatically adjust to changing water levels, maintaining consistent freeboard height relative to the water surface. In essence, satellite evidence validates the engineering logic behind maritime urbanism, why traditional seawalls and land reclamation are no longer viable long-term. Seawalls have long been the first line of defense against coastal flooding. Massive reinforced concrete barriers, revetments, and breakwaters are engineered to resist hydrostatic pressure and wave impact forces. However, modern climate patterns are exposing their limitations. First, seawalls reflect wave energy rather than dissipate it. This reflection increases scouring at the base, accelerating seabed erosion. Over time, undermining weakens the structural integrity of the wall. Second, extreme weather events, cyclones, and superstorms generate surge levels that exceed original design assumptions. Designing for increasingly rare return periods, like 1 in 500-year storms, dramatically increases construction cost and carbon footprint. Third, land reclamation projects require extensive soil stabilization, sand filling, and deep foundation systems. In delta regions with compressible clay deposits, long-term settlement becomes inevitable. Continuous maintenance becomes economically unsustainable. Take, for example, Tokyo and New York City, both of which have invested heavily in coastal protection. While engineering efforts are impressive, the financial and environmental costs are immense and still not future-proof against accelerating sea level rise. Additionally, rigid coastal barriers disrupt marine ecosystems, sediment transport cycles, and tidal flow patterns. This can worsen erosion elsewhere along the coastline. From a structural systems perspective, seawalls represent a static solution to a dynamic problem. They assume that water levels can be permanently contained. But as global baselines rise, containment becomes progressively more complex and expensive. Floating infrastructure, by contrast, does not resist rising water, it rises with it. Instead of increasing wall height every few decades, buoyant platforms maintain structural elevation automatically through hydrostatic equilibrium. Thus, the shift from rigid defense to adaptive design becomes not only logical but inevitable. From fighting water to living with it, the rise of maritime urbanism. The concept of maritime urbanism challenges centuries of land-centric city planning. Instead of reclaiming land or fortifying coastlines, engineers design habitable environments directly on water surfaces. Floating architecture is not new. Traditional floating villages have existed for centuries. However, scaling this concept to urban density requires advanced civil and marine engineering integration. Modern floating cities rely on modular honeycomb pontoons for distributed buoyancy, reinforced composite materials for corrosion resistance, dynamic mooring systems that absorb wave energy, flexible utility networks for water, power, and waste. The honeycomb pontoon configuration is particularly critical. By dividing large platforms into interconnected hexagonal buoyant cells, engineers achieve redundancy, enhanced stability, and improved load distribution. If one compartment is compromised, the entire structure remains operational. Dynamic mooring systems using tension leg anchors or semi-taut moorings allow controlled horizontal movement while preventing drift. This reduces structural stress during tidal fluctuations and storm surges. Countries like Netherlands, known for advanced water management strategies, are actively researching floating residential developments. Engineering firms are prototyping floating neighborhoods that integrate renewable energy systems and self-sustaining infrastructure. From a hydrostatic standpoint, the key lies in maintaining proper metacentric height to ensure roll stability under wave excitation. Structural modeling must incorporate wave structure interaction, fatigue analysis, and corrosion life cycle design. Maritime urbanism represents a philosophical shift in civil engineering, not dominance over nature, but intelligent coexistence. Floating infrastructure does not surrender to rising seas. It adapts, stabilizes, and evolves with them. The buoyancy stability paradox. When we speak about floating cities, the first engineering question that arises is simple yet profound. If something floats, can it remain stable under variable urban loads? This is what we call the buoyancy stability paradox. In conventional marine engineering, buoyancy ensures flotation, but stability ensures survivability. For floating urban infrastructure, both must be optimized simultaneously at an unprecedented scale. Buoyancy, governed by Archimedes' principle, states that a body immersed in fluid experiences an upward force equal to the weight of the displaced fluid. However, in large-scale floating platforms supporting buildings, vehicles, utilities, and dynamic human occupancy, flotation alone is insufficient. Stability becomes the controlling design parameter. Unlike ships, which are designed for mobility and forward propulsion, floating cities must behave as semi-permanent, quasi-static structural systems. They must resist rotational instability roll, pitch, and yaw, differential settlement effects due to uneven loading, and dynamic forces induced by waves, wind, and tidal surges. The paradox lies in this. Increasing buoyancy through larger displacement volumes may enhance load carrying capacity, but can simultaneously reduce metacentric stability if the geometry is not optimized. Professional civil engineers must analyze hydrostatic equilibrium conditions, ensuring that the center of gravity G, center of buoyancy B, and metacenter M maintain a stable relationship under both static and dynamic loading. The metacentric height GM must remain positive and sufficiently large to prevent capsizing tendencies. Moreover, floating cities face unique urban load complexities, moving crowds, traffic clusters, localized infrastructure loads, and high-rise superstructures. These loads are neither uniform nor constant. Therefore, solving the buoyancy stability paradox requires integrating marine hydrodynamics, structural engineering, geotechnical analogs, and advanced materials science. Only through modular platform geometry, distributed buoyancy systems, and dynamic anchoring can floating cities achieve the stability required for permanent habitation. Hydrostatic equilibrium and why traditional ship designs fail as permanent urban foundations. Hydrostatic equilibrium is achieved when the upward buoyant force equals the downward gravitational force acting on a floating body. In naval architecture, ships are designed to maintain this balance while moving through water. However, ship stability criteria differ fundamentally from the requirements of floating urban foundations. Traditional ships are optimized for forward propulsion efficiency, minimal drag resistance, controlled roll response, flexible loading conditions, cargo distribution changes. Their hull shapes are typically streamlined with curved sections that reduce hydrodynamic resistance. While this geometry is ideal for movement, it is not ideal for stationary urban stability. For permanent floating cities, the structural system must behave more like a floating raft than a vessel. Ships rely heavily on ballast systems to adjust stability dynamically. In contrast, floating cities cannot depend on continuous ballast correction for everyday urban load variations. Consider cruise liners or large maritime vessels. Even massive ships such as those operated by Royal Caribbean International experience noticeable roll motions during moderate wave conditions. While acceptable for transportation, such motion would be intolerable for residential or commercial urban life. Furthermore, ships are designed with high superstructures above the waterline, raising the center of gravity. This is manageable because the hull form and ballast compensate dynamically. But for floating urban platforms supporting multi-story buildings, excessive vertical mass concentration can reduce metacentric height and increase overturning risk. Urban infrastructure also introduces rigid vertical loads columns, shear walls, and core systems that behave differently from flexible ship superstructures. The response to wind-induced overturning moments must be considered alongside hydrostatic restoring forces. Therefore, traditional ship hull designs are insufficient for floating cities. Instead, wide-beam, flat-bottomed, multicellular pontoon systems offer greater transverse stability, reduced roll amplitude, and enhanced load distribution. In summary, hydrostatic equilibrium for floating cities must prioritize long-term structural stability, not navigational performance. That distinction fundamentally separates maritime transport engineering from maritime urban engineering. Modular honeycomb pontoons and load distribution under uneven population density. One of the most innovative solutions to the buoyancy stability paradox is the use of modular honeycomb pontoon systems. Unlike single-hull floating platforms, honeycomb configurations divide the base into multiple interconnected buoyant cells arranged in hexagonal or grid-based geometry. Why honeycomb? Hexagonal geometry provides efficient space utilization, structural redundancy, and multi-directional load transfer. Each cell functions as an independent buoyant chamber. When combined, they create a distributed flotation network rather than a single monolithic buoyant volume. In real urban scenarios, load distribution is never uniform. Imagine a floating city district where a stadium fills with 40,000 people. A commercial zone experiences peak occupancy. Residential towers vary in population density. Construction equipment concentrates temporarily in one zone. If a single large pontoon supports all loads, uneven distribution may cause tilting or differential submergence. However, in a honeycomb system, localized loading increases displacement primarily in adjacent cells rather than affecting the entire platform. Each module can be designed with reinforced concrete or composite shell, internal watertight compartments, integrated utility corridors, load transfer beams connecting adjacent cells. When a localized load increases, the affected cells displace additional water, generating proportional buoyant force. Surrounding cells redistribute stresses through structural connectors, maintaining overall platform equilibrium. This modularity also enhances resilience. If one compartment is damaged due to collision or fatigue cracking, adjacent compartments maintain flotation integrity. This redundancy mirrors fail-safe principles used in offshore platforms and bridge engineering. Countries such as Netherlands have pioneered floating residential prototypes using modular platforms that demonstrate remarkable transverse stability under variable loads. From a structural analysis perspective, engineers must model load combinations, dead load plus live load plus environmental load, differential buoyancy response, Shear transfer between modules. Fatigue due to cyclic wave loading. The honeycomb pontoon system transforms floating cities from fragile floating decks into robust, scalable, and adaptable structural foundations capable of supporting complex urban ecosystems. Center of gravity versus center of buoyancy during massive tidal surges. The stability of any floating structure depends on the geometric relationship between three critical points. 1. Center of gravity G. 2. Center of buoyancy B. 3. Metacenter M. The center of gravity represents the resultant point of all downward forces acting on the structure, including superstructures, utilities, occupants, and equipment. The center of buoyancy represents the centroid of displaced water volume. Under calm conditions, G and B align vertically. However, during tidal surges or wave-induced tilting, the submerged volume changes shape. This shifts the center of buoyancy laterally. The intersection of vertical lines through successive buoyancy centers defines the metacenter. For stable equilibrium, the metacenter must lie above the center of gravity. The vertical distance between the metacentric height Gm is a primary stability indicator. During massive tidal surges, floating cities must handle sudden changes in water elevation, wave crest and trough differentials, lateral wind pressure on superstructures, dynamic impact forces. If the center of gravity rises excessively due to tall buildings or concentrated rooftop loads, Gm reduces. A small GM results in slow, large amplitude rolling, dangerous for structural systems and occupant comfort. Therefore, floating city design incorporates low-profile structural bases, distributed mass rather than vertical concentration, heavy infrastructure, water tanks, mechanical systems placed near deck level, wide platform footprints to increase riding moments, advanced computational fluid dynamics CFD simulations model wave structure interaction during extreme events. Offshore engineering practices used in oil platforms operated by organizations such as Shell plc provide valuable insight into dynamic stability under surge conditions. The ultimate goal is controlled adaptability. As tides rise, the entire platform ascends uniformly. As waves induce tilt, restoring moments generated by buoyancy counteract overturning forces. By carefully managing the relationship between G, B, and M, floating cities can remain level, secure, and structurally sound even under the most severe tidal disturbances. Advanced material science for longevity. If floating cities are to function as permanent urban ecosystems rather than experimental prototypes, material durability becomes the defining factor. Unlike conventional terrestrial structures, floating infrastructure is continuously exposed to aggressive marine environments, high salinity, chloride penetration, cyclic wetting and drying, ultraviolet radiation, biofouling, and constant dynamic loading. Over decades, these environmental stressors degrade traditional materials at accelerated rates. Historically, marine structures relied on reinforced concrete and structural steel. While both materials have proven strength and versatility, their long-term durability in high salinity environments presents challenges. Chloride ions penetrate concrete cover, initiating corrosion in reinforcement bars. Steel components require continuous protective coatings and cathodic protection systems. Maintenance cycles become expensive and technically demanding, particularly in deep water conditions. Advanced materials science in 2026 focuses on extending life cycle performance rather than merely increasing initial strength. The goal is to achieve 75 to 100-year service life with minimal intervention. This requires integrating corrosion-resistant composites, fiber-reinforced polymers (FRP), nano-enhanced concrete matrices, and hybrid material systems. Marine engineering research institutions and innovation programs supported by organizations such as MIT are developing high-performance composites that outperform traditional steel in corrosion resistance while maintaining comparable tensile capacity. These materials significantly reduce life cycle carbon emissions by lowering maintenance frequency. Additionally, the integration of smart materials, self-healing polymers, and bioreceptive coatings transforms floating platforms into adaptive systems that strengthen over time instead of degrading. For professional civil engineers, this shift demands new design codes, new fatigue analysis methodologies, and new understanding of composite behavior under cyclic marine loading. Durability is no longer an afterthought, it is the foundation of floating urban resilience. Transitioning to 2026 grade corrosion-resistant composites. In high salinity marine environments, chloride-induced corrosion is the primary cause of structural degradation. Traditional carbon steel reinforcement, even with protective coatings, eventually experiences oxidation when chloride ions penetrate protective layers. This leads to cracking, spalling, and structural weakening. For floating cities designed to operate continuously offshore, such vulnerability is unacceptable. The 2026 transition involves replacing conventional reinforcement and exposed steel elements with advanced corrosion-resistant composites. Glass fiber-reinforced polymer (GFRP), carbon fiber-reinforced polymer (CFRP), and basalt fiber composites are increasingly used as primary structural reinforcement alternatives. Unlike steel, FRP materials do not rust. Their tensile strength-to-weight ratio is significantly higher, reducing structural self-weight and lowering the center of gravity, an important factor in floating stability. Reduced weight directly enhances buoyancy efficiency and improves metacentric height. Hybrid composite concrete systems now incorporate nanosilica additives, ultra-high-performance concrete UHPC, and geopolymer binders that resist chloride penetration far better than traditional Portland cement concrete. These materials exhibit lower permeability and improved microstructural density. Marine-grade epoxy matrices used in composite systems are designed to resist ultraviolet degradation and hydrolysis. Additionally, sacrificial anode systems are being supplemented with intelligent corrosion monitoring sensors embedded within structural members, allowing predictive maintenance rather than reactive repair. Research collaborations supported by organizations such as NASA have advanced composite technologies originally developed for aerospace applications. These high-performance materials are now being adapted for civil marine infrastructure. However, composite materials introduce new challenges engineers must consider: long-term creep behavior, fire resistance and thermal expansion compatibility, connection detailing between composite and concrete, fatigue performance under cyclic wave loading. Design codes are evolving to incorporate these materials into marine structural standards. The shift from steel-dominant systems to composite-integrated structures represents one of the most transformative changes in floating city engineering. Durability, weight reduction, and life cycle economy are now driving structural material selection. Bioreceptive textures and coral strengthen structural bases. One of the most fascinating innovations in floating city infrastructure is the concept of bioreceptive surfaces, engineered textures designed to encourage marine life growth rather than prevent it. Traditionally, marine engineering viewed biofouling as a threat. Barnacles, algae, and coral accumulation were considered detrimental due to added weight and drag. However, the paradigm is shifting. Instead of resisting marine ecosystems, floating cities can integrate ecological engineering principles to strengthen their submerged structures over time. Bioreceptive concrete incorporates microtextured surfaces and mineral compositions that promote coral larval attachment. calcium-rich formulations and pH-balanced coatings encourage marine calcification. Over time, coral colonies attach and grow, forming a natural reinforcement layer around submerged pontoons. This concept is inspired by artificial reef projects and coastal restoration initiatives supported by organizations like National Oceanic and Atmospheric Administration, which demonstrate how engineered substrates can accelerate coral regeneration. From a structural standpoint, coral growth can increase surface roughness, improving hydrodynamic damping, provide additional protective layering against erosion, enhance local marine biodiversity, improve structural integration with surrounding ecosystems. Careful structural modeling is required to account for additional dead load from marine growth. However, this load is typically distributed and incremental, allowing gradual adjustment in buoyancy calculations. Bioreceptive materials also improve environmental acceptance of floating cities. Instead of displacing marine life, platforms become ecological hubs, supporting reef systems and fish populations. For civil engineers, this introduces interdisciplinary collaboration with marine biologists and environmental scientists. Material selection must balance structural strength, chemical stability, and ecological compatibility. Floating cities thus evolve into hybrid infrastructure, part engineered structure, part living marine ecosystem strengthened naturally over time rather than deteriorating. Self-healing polymers in pontoon joints for deep water durability. Pontoon joints are critical stress concentration zones in modular floating platforms. These joints experience cyclic tensile, compressive, and shear forces due to wave action, thermal expansion, and dynamic loading. Over time, microcracks develop within connection materials, potentially compromising watertight integrity and structural continuity. To minimize long-term maintenance costs, engineers are integrating self-healing polymer technologies into pontoon joint systems. These advanced polymers contain microencapsulated healing agents or reversible chemical bonds that activate when cracks form. When microcracks appear, embedded capsules rupture, releasing bonding agents that chemically seal the crack. Other polymer systems rely on thermally reversible cross-linking reactions that reform molecular bonds after mechanical damage. Research programs supported by institutions such as Stanford University have demonstrated polymer systems capable of restoring up to 90% of original tensile strength after crack formation. In floating city applications, self-healing materials are used in flexible expansion joints between pontoon modules, waterproof membranes in submerged compartments, protective coatings on structural connectors, composite joint interfaces. The economic benefits are substantial. Offshore maintenance operations are expensive due to access constraints, specialized equipment, and safety risks. By embedding autonomous repair capability into the structure itself, life cycle costs are significantly reduced. From a structural reliability perspective, self-healing systems enhance redundancy. Small defects do not propagate into catastrophic failures. Instead, they are contained at microscale levels. Engineers must still consider long-term performance limits, healing cycle frequency, and environmental compatibility. However, early field deployments in offshore energy platforms show promising results. By integrating corrosion-resistant composites, bioreceptive surfaces, and self-healing polymers, floating cities transition from vulnerable marine structures to resilient, adaptive infrastructure systems capable of surviving decades in harsh ocean environments. Dynamic mooring and infrastructure. Floating cities cannot rely on conventional fixed foundations such as pile caps, raft foundations, or caisson systems anchored into stable soil strata. Instead, they depend on advanced mooring technologies that provide positional stability while allowing controlled vertical and horizontal movement. The challenge lies in balancing restraint and flexibility. Too rigid a mooring system transfers excessive stress to the floating platform during storm events. To flexible, a system risks drift, collision between modules, or excessive oscillation. Dynamic mooring systems are inspired by offshore oil and gas platforms, yet they must operate with far greater precision for urban environments. Unlike industrial platforms, floating cities must ensure occupant comfort, utility continuity, and structural reliability under frequent tidal fluctuations and extreme weather events. Modern mooring configurations include tension leg platforms (TLP), semi-taut mooring lines, catenary anchor systems, hybrid elastic polymer tether systems. These systems use high-strength synthetic fiber ropes, corrosion-resistant chain segments, and deep-sea anchors embedded into seabed strata. However, the real breakthrough in 2026 lies in integrating real-time monitoring, predictive analytics, and AI-driven tension adjustment systems. Instead of being passive anchoring elements, mooring systems now function as adaptive structural components. Sensors measure wave height, wind velocity, current speed, and platform displacement. Algorithms adjust cable tension accordingly, distributing forces across multiple anchor points. This transforms floating cities from loosely anchored structures into intelligent, self-adjusting infrastructure networks capable of withstanding tidal surges and extreme storm loading while maintaining stability and alignment. AI-driven mooring systems and real-time tension adjustment. Traditional mooring systems are designed based on worst-case environmental loading scenarios using deterministic design methods. Engineers calculate maximum expected wave height, current velocity, and wind pressure, then size mooring lines accordingly. While safe, this approach results in conservative overdesign and inefficient stress distribution during moderate conditions. In contrast, AI-driven mooring systems operate dynamically. High-precision sensors embedded in anchor points and tether lines continuously monitor wave amplitude and frequency, platform roll, pitch, and yaw angles, cable strain and elongation, seabed anchor movement. These data streams are processed through predictive control algorithms that anticipate force spikes before they peak. Actuated winches and smart tensioning devices adjust cable lengths and stiffness in real time, redistributing loads evenly across the mooring network. This technology draws inspiration from advanced offshore installations, such as those deployed by Equinor, where floating energy platforms must survive severe North Sea conditions. For floating cities, AI-driven mooring provides several critical advantages. 1. Reduced peak stress in structural joints. 2. Improved comfort by minimizing excessive sway. 3. Increased fatigue life of tether components. 4. Enhanced resilience during storm surges. In extreme weather, the system can temporarily increase stiffness to limit horizontal displacement. During calm conditions, tension is relaxed to reduce material fatigue. Engineers must integrate structural dynamics modeling, machine learning algorithms, and marine geotechnical anchoring analysis to ensure system reliability. Redundant control systems are essential to prevent failure during power interruptions. The shift from passive anchoring to intelligent mooring marks a fundamental evolution in marine civil engineering. Foundations are no longer static, they are responsive, predictive, and adaptive. Flexible utility umbilicals for moving city modules. A floating city is not a single rigid block, it is a modular assembly of interconnected platforms. As these modules respond to tides, waves, and dynamic mooring adjustments, slight relative movement occurs between them. Traditional rigid utility connections would fracture under such motion. To address this, engineers implement flexible infrastructure umbilicals. These are bundled, high-performance conduits designed to transfer power, potable water, wastewater, communication data, and sometimes hydrogen fuel between modules without compromising structural independence. Flexible umbilicals are adapted from subsea energy systems used in offshore production platforms. They consist of multi-layer polymer sheathing, corrosion-resistant metallic reinforcement, pressure-resistant internal tubing, Fiber optic data cores. The design must account for repeated bending cycles, torsional stress, and long-term fatigue due to wave-induced oscillations. In floating urban systems, utility umbilicals are routed through articulated joints equipped with shock absorbers and expansion compensators. These joints ensure continuous service even when adjacent modules experience differential motion. For power transmission, floating grids may incorporate high-voltage subsea cables similar to those used in offshore wind farms developed by companies such as Siemens Energy. These cables are designed for marine durability and electromagnetic shielding. Water and wastewater systems utilize flexible HDPE or composite pipelines with leak detection sensors. Real-time monitoring ensures rapid identification of microfractures before system failure. Data transfer infrastructure integrates fiber optic cores capable of supporting high-bandwidth communication networks required for smart city operation. From a civil engineering perspective, the integration of flexible utilities demands multidisciplinary coordination between structural, electrical, mechanical, and marine engineers. Proper detailing at connection nodes is essential to avoid stress concentration and fatigue cracking. Flexible umbilicals enable floating cities to behave like living organisms. Modules move independently, yet remain seamlessly connected through resilient infrastructure networks. Pilot projects in the Maldives and Bizen as scalable blueprints. Theoretical models of floating cities are now transitioning into real-world pilot projects. Two of the most significant examples are located in Maldives and Bizen. The Maldives Floating City project is being developed as a climate-adaptive residential community designed to accommodate thousands of residents. The nation faces existential risk due to rising sea levels, making floating infrastructure a practical necessity rather than experimental ambition. The project integrates modular floating platforms arranged in lagoon-friendly configurations. Mooring systems allow vertical tidal adjustment while maintaining lateral stability. Renewable energy integration, desalination plants, and decentralized wastewater treatment systems are incorporated into each module. Similarly, Bizen is advancing a floating district concept supported by international collaboration and smart city integration. The design emphasizes scalable modules that can expand outward without requiring seabed reclamation. Renewable energy sources such as offshore solar arrays and wave energy converters are being evaluated to support autonomous power grids. These pilot initiatives demonstrate several engineering breakthroughs: scalable modular expansion, integrated dynamic mooring systems, renewable marine-based power generation, smart grid interconnectivity. For civil engineers, these projects serve as real-world laboratories. Structural performance, environmental integration, and life cycle maintenance strategies are being tested under operational conditions. Most importantly, these pilots show that floating infrastructure is not speculative, it is implementable. Lessons learned from the Maldives and Bizen can inform future developments in coastal regions worldwide. Floating cities are transitioning from concept renderings to engineered realities. And as these pilot projects scale, they will define the standards for resilient ocean-based infrastructure systems capable of supporting future global populations. Flexible utility umbilicals for moving city modules. A floating city is not a single rigid block, it is a modular assembly of interconnected platforms. As these modules respond to tides, waves, and dynamic mooring adjustments, slight relative movement occurs between them. Traditional rigid utility connections would fracture under such motion. To address this, engineers implement flexible infrastructure umbilicals. These are bundled, high-performance conduits designed to transfer power, potable water, wastewater, communication data, and sometimes hydrogen fuel between modules without compromising structural independence. Flexible umbilicals are adapted from subsea energy systems used in offshore production platforms. They consist of multi-layer polymer sheathing, corrosion-resistant metallic reinforcement, pressure-resistant internal tubing, Fiber optic data cores. The design must account for repeated bending cycles, torsional stress, and long-term fatigue due to wave-induced oscillations. In floating urban systems, utility umbilicals are routed through articulated joints equipped with shock absorbers and expansion compensators. These joints ensure continuous service even when adjacent modules experience differential motion. For power transmission, floating grids may incorporate high-voltage subsea cables similar to those used in offshore wind farms developed by companies such as Siemens Energy. These cables are designed for marine durability and electromagnetic shielding. Water and wastewater systems utilize flexible HDPE or composite pipelines with leak detection sensors. Real-time monitoring ensures rapid identification of microfractures before system failure. Data transfer infrastructure integrates fiber optic cores capable of supporting high-bandwidth communication networks required for smart city operation. From a civil engineering perspective, the integration of flexible utilities demands multidisciplinary coordination between structural, electrical, mechanical, and marine engineers. Proper detailing at connection nodes is essential to avoid stress concentration and fatigue cracking. Flexible umbilicals enable floating cities to behave like living organisms. Modules move independently, yet remain seamlessly connected through resilient infrastructure networks. Pilot projects in the Maldives and Bizen as scalable blueprints. Theoretical models of floating cities are now transitioning into real-world pilot projects. Two of the most significant examples are located in Maldives and Bizen. The Maldives Floating City Project is being developed as a climate-adaptive residential community designed to accommodate thousands of residents. The nation faces existential risk due to rising sea levels, making floating infrastructure a practical necessity rather than experimental ambition. The project integrates modular floating platforms arranged in lagoon-friendly configurations. Mooring systems allow vertical tidal adjustment while maintaining lateral stability. Renewable energy integration, desalination plants, and decentralized wastewater treatment systems are incorporated into each module. Similarly, Bizen is advancing a floating district concept supported by international collaboration and smart city integration. The design emphasizes scalable modules that can expand outward without requiring seabed reclamation. Renewable energy sources such as offshore solar arrays and wave energy converters are being evaluated to support autonomous power grids. These pilot initiatives demonstrate several engineering breakthroughs: scalable modular expansion, integrated dynamic mooring systems, renewable marine-based power generation, smart grid interconnectivity. For civil engineers, these projects serve as real-world laboratories. Structural performance, environmental integration, and life cycle maintenance strategies are being tested under operational conditions. Most importantly, these pilots show that floating infrastructure is not speculative, it is implementable. Lessons learned from the Maldives and Bizen can inform future developments in coastal regions worldwide. Floating cities are transitioning from concept renderings to engineered realities. And as these pilot projects scale, they will define the standards for resilient ocean-based infrastructure systems capable of supporting future global populations. The future of sovereign maritime states. Floating cities are not merely engineering responses to rising sea levels, they represent the potential birth of sovereign maritime states. When infrastructure becomes mobile, adaptive, and ocean-based, the geopolitical, economic, and legal frameworks of civilization begin to evolve. Traditionally, sovereignty has been tied to landmass. Borders are drawn on fixed geography. But floating urban systems introduce the possibility of semi-autonomous or fully autonomous maritime jurisdictions operating beyond vulnerable coastlines. From a civil engineering standpoint, sovereignty begins with infrastructure independence. A floating state must possess its own structural foundation, energy systems, water production, food cultivation, waste recycling, communication networks, and governance facilities. Engineering is no longer just about supporting buildings, it becomes the backbone of national resilience. International maritime law, including frameworks monitored by organizations such as United Nations, currently governs territorial waters and exclusive economic zones. However, floating cities operating in international waters introduce new policy considerations regarding taxation, environmental responsibility, and political identity. The engineering feasibility of sovereign maritime states depends on structural permanence, durability, and economic viability. Modular platforms must withstand decades of marine exposure. Mooring systems must allow repositioning when required. Utility grids must function independently from terrestrial networks. For civil engineers and planners, this represents a paradigm shift. Infrastructure is no longer anchored permanently to land. Instead, it becomes dynamic, scalable, and geopolitically transformative. Floating states can redefine resilience not as resistance to environmental forces, but as the freedom to adapt geographically and economically. Socio-economic impact of mobile cities. Mobile floating cities introduce a revolutionary socio-economic model. Unlike traditional urban centers fixed in place, these cities can relocate in response to economic opportunities, environmental risks, or geopolitical changes. This mobility transforms infrastructure into a strategic asset. For example, if trade routes shift due to new maritime corridors or climate-induced Arctic openings, a floating commercial hub could reposition itself closer to emerging economic zones. Instead of constructing entirely new ports and logistics networks, the city itself moves to align with global trade patterns. Similarly, if a region becomes environmentally unstable due to cyclones, sea level anomalies, or marine ecosystem degradation, the city can relocate to safer waters. This adaptability reduces disaster recovery costs and long-term infrastructure losses. From a labor and employment perspective, floating cities may foster specialized marine industries, offshore renewable energy, aquaculture, desalination technology, and marine biotechnology. Economic clustering could occur around floating innovation hubs, attracting engineers, scientists, and entrepreneurs. Urban mobility also influences real estate economics. Property ownership models may shift toward modular leasing frameworks rather than land-based speculation. Infrastructure financing models could evolve into maritime bonds or ocean-based development funds. However, engineers must design structural systems capable of safe relocation. Modular segmentation, detachable mooring systems, and flexible utility connectors are essential to enable controlled repositioning without service disruption. Global economic organizations such as World Economic Forum have highlighted the importance of climate-adaptive infrastructure in maintaining economic stability. Floating cities represent one of the most proactive approaches to climate resilience. In essence, mobile cities convert vulnerability into flexibility. They provide economic continuity even as environmental conditions evolve. Scalability of floating districts into fully autonomous, zero-carbon civilizations. Scalability is the defining engineering principle that determines whether floating districts remain experimental coastal projects or evolve into fully autonomous maritime civilizations. A single floating neighborhood demonstrates structural feasibility. However, a network of interconnected, energy-independent, resource-efficient districts demonstrates systemic sustainability. The transition from district to civilization requires infrastructure that is modular, redundant, and capable of exponential expansion without destabilizing the base platform. The scalability model begins with modular replication. Each floating district is designed as a structurally independent unit, supported by honeycomb pontoon foundations, dynamic mooring systems, and integrated utility corridors. These districts function as plug-and-play infrastructure blocks. When population demand increases, new modules are attached laterally without overloading existing buoyancy systems. Structural expansion does not require dredging, land reclamation, or permanent seabed modification. Energy autonomy is central to zero-carbon scalability. Floating civilizations have direct access to marine renewable energy resources, including offshore wind, floating photovoltaic arrays, tidal turbines, and wave energy converters. Hybrid microgrids distribute power across districts while maintaining decentralized redundancy. Lessons from large-scale offshore wind integration projects supported by International Renewable Energy Agency demonstrate how renewable heavy grids can achieve long-term reliability. Water independence is achieved through renewable power desalination systems using reverse osmosis and next-generation membrane technologies. Wastewater is recycled through closed-loop treatment plants, reducing fresh water demand. Organic waste is converted into bioenergy through anaerobic digestion, contributing to circular resource management. Urban food production integrates vertical farming, hydroponics, and aquaponics within climate-controlled structures. By reducing reliance on terrestrial supply chains, floating cities enhance food security and minimize transportation emissions. From a structural engineering perspective, scalability demands careful load forecasting. As districts expand vertically and horizontally, engineers must continuously assess metacentric height and overall stability, energy load distribution, utility redundancy, emergency response resilience. Digital twin modeling allows real-time simulation of expansion impacts before physical construction begins. Ultimately, scalability ensures that floating districts evolve into fully autonomous, zero-carbon civilizations, not as isolated experiments, but as replicable, resilient urban ecosystems capable of supporting future generations sustainably on the world's oceans, turning a climate threat into a frontier for human expansion. Throughout history, human civilization has expanded by overcoming environmental barriers, mountains, deserts, and oceans. Today, rising sea levels present a new barrier. Yet, with advanced marine engineering, that barrier transforms into opportunity. Floating cities convert ocean surfaces once viewed primarily as transportation corridors into habitable space. Considering that oceans cover more than 70% of the planet's surface, the spatial potential is immense. From a civil engineering perspective, the ocean becomes a new foundation medium. Instead of soil-bearing capacity, engineers calculate buoyant displacement. Instead of settlement analysis, they assess hydrostatic equilibrium. Instead of rigid foundations, they design adaptive platforms. This frontier also encourages technological innovation. Material science, renewable energy integration, marine ecology, artificial intelligence, and smart city systems converge in one environment. Moreover, floating cities reduce pressure on overcrowded coastal megacities. As land scarcity intensifies, ocean-based expansion offers additional living space without deforestation or terrestrial ecosystem destruction. The philosophical transformation is profound. Rather than defending coastlines endlessly with higher seawalls, humanity adapts by expanding into water environments responsibly. Organizations like United Nations Environment Program advocate for sustainable climate adaptation strategies. Floating infrastructure embodies proactive adaptation rather than reactive defense. In conclusion, resilient floating foundations do more than solve a climate crisis, they redefine civilization's relationship with the planet. Rising seas no longer signify retreat. They signal expansion into a new engineered frontier, a real-world example of a scalable floating city model. One of the strongest real-world examples aligning with the vision of scalable, autonomous floating civilizations is the Ocean X Bizen prototype in Bizen. developed in collaboration with UN Habitat and the ocean engineering company Oceanix. This project is not just conceptual architecture, it is a fully engineered floating urban district designed for long-term climate adaptation. Oceanix Bizen is structured around modular hexagonal platforms, directly reflecting the honeycomb pontoon strategy discussed earlier. Each platform is engineered to support mixed-use development, residential towers, research hubs, agricultural greenhouses, and public spaces while maintaining independent buoyancy and stability. The modules interconnect to form larger districts, demonstrating scalability without compromising hydrostatic equilibrium. The city integrates zero-carbon energy systems, including floating solar panels and on-site renewable microgrids. Desalination units powered by renewable energy provide freshwater independence. Waste is processed using circular systems to minimize emissions and landfill dependency. The platform is designed to withstand typhoon-level storm surges while adjusting vertically with tidal fluctuations. What makes this project particularly important for civil engineers is its practical validation of theoretical principles. Modular expansion capability, dynamic mooring resilience, renewable powered infrastructure, integrated marine ecosystem preservation. Oceanix Bizen proves that floating urban districts are not speculative science fiction. They are engineering realities under development. It serves as a blueprint for coastal nations facing rising sea levels, demonstrating that ocean-based urban expansion can be structurally sound, environmentally responsible, and economically viable. This example bridges the gap between concept and implementation, turning maritime urbanism into a scalable civil engineering solution. As civil engineers, we are not merely builders of structures, we are architects of humanity's future. Rising sea levels represent one of the greatest infrastructure challenges of our time. But as we've explored today, the solution is not limited to taller seawalls or endless land reclamation. The solution may lie in reimagining the very foundation on which civilization stands. Floating cities demonstrate how engineering innovation, modular, honeycomb pontoons, advanced composites, AI-driven mooring systems, renewable microgrids can transform a climate threat into a new frontier of opportunity. The oceans cover more than 70% of our planet. Instead of retreating from them, we can responsibly expand into them, designing resilient, adaptive, and sustainable maritime civilizations. If you are a civil engineer, student, or infrastructure professional, this is your era. The future of urban development may not be built on land, but on water. This is Civil Engineering Edge, where we don't just study the future of infrastructure, we engineer it.